Yeah, okay, welcome. So it was a bit by chance that we arranged this research day because I saw that there was a communication in Japanese on Twitter, then now X, and so I started to intervene. And then from this, the idea came, why not collaborate on the stellar feeling and also on the liquid metal that Ratul is performing within the FAO Sublime project. And then we performed it under also the BrIAS event. So that's why Professor Hiroki Ishizuka is now here, or he came back for 1 week to finish some last experiments with Ratul. So he's now both preparing the paper, but we get already a glimpse of what both were doing in our lab. So please take the floor.
Hi, Bram, thank you for your kind introduction. So I'm Hiroki Ishizuka from Osaka University, but recently the name of my university is changed. I wrote the Osaka University, but the name was changed last week. The University of Osaka, that is a wrong name, sorry. So I'm happy to get the chance to present at here. So today I'll talk about the topics related to the tactile sense. I have studied these kind of topics for the 10 years or more. Okay, these are topics. So first, I'll explain my personal information. So I was born in the north part of Japan, Niigata Prefecture. Then, after I graduated high school, I moved to the Kanagawa Prefecture near Tokyo. Then I joined the Meiji University. After I got a bachelor, I went to master course of Meiji University. To get Ph.D, I moved to Keio University in Kanagawa Prefecture. So last week, I attended a conference here between the Belgium and the Waseda University. Meiji University and the Waseda University and the Keio University are famous private universities in Tokyo area in Japan. So they are rival. Sometimes they compete for the baseball game or the number of the candidate of the entrance examination. So last week, I felt a kind of fate here. After I got PhD, so I joined Kagawa University. Kagawa is the smallest prefecture in Japan, and the Kagawa University is a national university. I worked there for 3 years, and then so I moved to the Osaka University. I have been in Osaka University for 6 years. So currently, I try to find a new position in another organization. So my purpose of the visiting here is the development of a soft robot using multi-self-healing materials. As Bram said, I tried the self-healing polymers and the liquid metal. Okay, here you can see the Belgium. Maybe here is Belgium, and here is Japan. So flight from Belgium to Japan takes, I think, at least 13 hours. So long flight. Yes, yes. And then, so I came here, I think the flight go from the United States side, past the North Pole, and came to the Belgium, maybe. So, yeah, this is the map of Japan. So Niigata, where I was born, is here, and the Kanagawa Prefecture is here. Maybe some of you visited Kanagawa Prefecture because the Kanagawa Prefecture includes Yokohama City, and the last ICRA was held in Kanagawa Prefecture, Yokohama. So some of you might visit it. And the Osaka is here. Osaka is famous for the foreign people because next to Kyoto. And the Kagawa is here. So Kanagawa and Osaka are famous to everyone, I think. But the Niigata and the Kagawa are not so famous. So I'll shortly explain the culture. Niigata is near from sea, and there are many mountains and cold. So Niigata is famous for the delicious seafood like raw fish or sushi, and also famous for the winter sports, skiing and snowboarding. Also, Niigata is famous for the rice. So there are nice rice alcohols. And Kagawa is famous for udon. So I went to Carrefour with Russell, and I went to the udon, and I checked the price of the company, and found the udon was from the Kagawa prefecture. So if you want to try the nice udon, please visit Kagawa. And also, there are spicy fried chicken and the art festival. The art festival is, I think, famous because my collaborator in the foreign country also knows this event. Okay. Next, I'll talk about the research. First, I'll talk about the research motivation and research interest. So my research motivation and research interest is how can we understand and utilize the mechanism of tactile sense. We usually use tactile sense, for example, touch object or search environment, and recognize the environment or object. However, we don't totally understand the mechanism of tactile sense. For example, how tactile afferents, which is a nerve to sense tactile sense, contributes to the tactile sense, or how skin contributes to the sense. So I want to reveal these questions and apply the findings from the mechanism, findings from the question, and apply them to the development of the better devices. For example, better tactile sensors, or better soft robot, or better tactile devices for virtual reality. Okay, next, I'll talk about the history, why I got such motivation. So when I was a PhD student, I was in the laboratory of the microfabrication, MEMS technology. There, I fabricated various tactile displays. For example, I developed a soft and flexible sheet-type tactile display. This device can present a vibrotactile stimulus to users. So user can feel vibration by touching the device. I use soft materials such as silicon rubber or conductive soft polymer to fabricate this device. I also focused on the interesting materials such as magnetorheological fluid. Magnetorheological fluid is a mixture of the iron particle and oil. So I encapsulated the liquid into the device and apply the magnetic field spatially. The device can spatially present the stiff spot like a tumor. So the device can applicable to the application such as remote palpation or medical application something. I also tried the fabrication of the soft material. For example, it is known that it is difficult to make a three-dimensional silicon membrane structure. To solve this problem, I use a liquid droplet as a mold. So I formed a thin silicon rubber membrane on the surface of the droplet, and after the membrane was cured, I removed the droplet, and I could get the droplet-shaped membrane like this. The membrane can be applicable to the application, such as soft robot or tactile devices. I found through these devices, so I faced a problem. Even if I use these kind of devices, it is impossible to reproduce tactile texture so realistically. And I mean, it is impossible to reproduce the tactile textures using these kind of devices perfectly. So to solve this problem, so I found one way, a use of simulation. If we can simulate the activity of tactile afferents using this kind of simulation, it is possible to simulate how we feel the texture or object or force or something. So this is an example of a simulation, and the name is finite element method analysis. This method is famous, and this method divides the object into small elements and apply the deformation to the object. Then, so each element deform. As a result, we can get the entire deformation of the object. Then, so I also faced another problem. So how can I use this method to my research? So I need to find a way of my research. Then, so I considered a lot, and I found 3 ways. One way is, as I said, I can use the simulation method to understand and simulate tactile sense using the simulation method on computer. If I can get good findings from the simulation, it is possible to develop better devices using the findings or novel materials. Also, if I could prepare new devices, it is possible to develop applications such as virtual reality or remote operation. From 3 ways, I found one research direction, so recording and presenting tactile sense. So recently, metaverse, that is a kind of the virtual reality technology, attracts interest of both researchers and the industry. So it is said the market of the metaverse will be huge in the future. I believe the nature of the metaverse is presenting sense, such as tactile or visual or auditory or and so on. And I believe the tactile sense is a powerful sense for the virtual reality, because as I said, we touch object to distinguish the object or environment. So we can feel the reality through tactile sense. So, but the problem is the current devices cannot record the tactile sense or present tactile sense, as I said. And I saw that understanding of and utilizing the tactile sense can solve this problem and will contribute to the development of the better devices. For this purpose, I conducted research for the 3 topics. One is simulation and measurement. In this side, I simulate the skin and the tactile afferent nerve using a computer. And to get a numerical model for the skin or nerve, I need to collect biological data. For this purpose, I also conducted an experiment for the biological data. For example, I developed a haptic display and it stimulates participants and gets brain data. And using these findings, I developed various sensors and actuators. For example, soft actuator or soft sensor. Using findings of the simulation and the measurement and the sensor and actuator, I also developed tactile displays for the virtual reality or remote operation. For example, I developed high-resolution tactile display using microfabrication technology or small force haptic device for the virtual reality using low boiling point liquid. Okay, next, I'll talk about each topics. First, I'll talk about the simulation and measurement. Inside our skin, so there are many tactile afferents, and there are many types of tactile afferents. For example, FA1 and the SA1, SA2, and FA2. The name of the afferent is name of the organ is FA1 is Meissner, and SA1 is Merkel, and SA2 is Ruffini, and also FA2. FA2 is Pachinian. And these tactile afferents encode tactile information, such as force direction or contacting shape or texture. This figure shows a famous result. In this experiment, force is applied to fingertip, but in different direction. Then the authors recorded the responses of tactile afferent, but at different location and different types. For example, SA1 here was recorded. Also, here was recorded. In the experiments, as I said, so different direction force was applied, and the P, U, D, and R and N direction is shown here was applied. From the results, it can be seen that the responses of tactile afferents were differ according to the direction of the force and the location. So human process this kind of information from tactile afferent and recognize tactile sense. So if we can simulate the activity of tactile afferent, it is possible to understand how we feel tactile sense, such as force or texture or object. Okay. For this purpose, I constructed a model for the simulation. As I said, finite element method analysis is a powerful tool to simulate the activity of tactile afferent, I believed. So before the experiment, before the research, I investigate the related works. This is a summary. Vertical axis shows the structure of skin, and the horizontal axis shows the stimulus pattern. From this summary, I found that this area was not investigated. So layered complex skin model and the stimulus to vibrotactile stimulus. So simulation of the tactile afferent to vibrotactile stimulus is important to develop tactile devices because these kind of devices provide vibration to users, and the user can feel the artificial surface texture or object through these devices. So simulation of this area is useful to develop the device. So I conducted the research. This is the outline of the model. So the model contains the skin, mechanical part, and the neural dynamic model part. So we use the two-dimensional skin model, layered skin model here, and apply the deformation to the skin, and calculate the stress inside the model. And the sampled stress at each tactile afferent location was substituted into the neural dynamic model. We use the integrate and fire model as a neural dynamic model. Integrate fire model is famous nerve model, and the structure is simple. We need to optimize the term of the model and the parameter of the model. So we use the biological data from another group to optimize the model. The model can output the membrane potential, which represents the activity of tactile afferent. So to verify the model, we conducted simulation. In the simulation, so we applied the vibrotactile stimulus to the model and monitor the output membrane potential. This time, so we applied the sinusoidal stimulus to the model. And this figure shows the result. SA and RA and PC means the type of tactile afferent. Sorry, a little bit different from the previous one. And the red dots show the firing timing of the simulation, and the black one shows the actual firing timing. So timing is important because when stimulus is applied to the tactile afferent, membrane potential is gradually increased. And at certain voltage, the membrane potential suddenly increased. And the increased membrane potential information is sent to the following nerves and finally reach brain. And we recognize the tactile sense. For this purpose, the timing of the firings is important for the tactile recognition, and we evaluated this point. So from the result, the timing of the firing is similar between the simulation result and the actual result. Also, we tried another vibration condition, such as a noise, vibrotactile stimulus, or diharmonic stimulus. in all cases, the timing were similar. From the results, we conclude that the model, we could construct its model, numerical model of the skin and tactile afferent well. Previously, we used two-dimensional skin model, but currently we are trying to apply three-dimensional skin model. So we mimic the structure and the shape and the mechanical property of skin, and developed this model. In future, we will apply this model to simulate complex, more complicated skin deformation, such as shear force or contact to texture or object. Okay. As I said, to construct the numerical model, we need to collect biological data. For this purpose, I also tried the biological data collection. We hypothesized that the tactile shape recognition and the visual shape recognition are conducted in the same area of brain. To investigate this hypothesis, we conducted experiment using functional MRI. In the fMRI, it is impossible to use magnetic materials. So I designed a new pneumatic actuator without magnetic material. See, the width of the actuator was maybe 1 centimeter. So I arranged this pneumatic actuator densely. There were 35 pneumatic actuators. The array of actuator could present the shape information to users, to their palm. So we set this device inside the MRI, and we also placed the control system, including the pneumatic compressor and the valve system outside of the room. Okay, we conducted experiment with 6 participants. The number of the participants was insufficient because this was a preliminary experiment. So in the experiment, we put the participants in the functional MRI, and we apply the magnetic field of 3 Tesla. In the experiment, we use the number and the character as a stimulus to the participant. So in the experiment, we we present this kind of stimulus to users through their eye or palm. And the pattern gradually presented to participants. For example, first present this line, and second this line, and third this line, and this line, and this line. After the simulation, we ask the participant to recognize and answer the presented stimulus. So the trial can be divided into 2 phases. One is the stimulus phase, and the another is the recognition and the answer phase. So we use the number of 0 to 9 and the character A to L. So we conducted 3 trials for each stimulus. Hi. Okay.
So are you actually stimulating in the shape of the digits and characters on the palm?
Yes.
Okay. And why did you choose this sort of like passive touch on the palm as opposed to something more intuitive with the active touch?
Shall we keep questions then so that we can take the microphone?
So questions at the end.
Okay. Okay, later. Please discuss later. Sorry. And okay. Sorry. Okay. In total, so we conducted about 50 trials. These figures show the result, and the left side shows the recognition accuracy of the tactile stimulus. The participant could recognize the stimulus correctly at the ratio of the 65%. The ratio was good. In the case of visual stimulus, the recognition ratio was much better because it is easy to distinguish through our eye. Some of the participants wrongly answered 5 and 9 and A and E. Because the shape of these characters and numbers are similar. So for the participant, it is difficult to distinguish these kind of the patterns. And the right side shows the result of the brain activity. This side shows the brain activity during the stimulus phase, and this side shows the brain activity during the recognition and the answer phase. Top side shows the response to the tactile stimulus, and the bottom side shows the response to visual stimulus. From the result, when stimulus was presented to the participant, somatosensory area was activated. On the other hand, during the recognition and the answer phase, backside of the brain was activated. There are IPS and LOC. So from the result, it might be said that the human use the same brain area to recognize the shape through eye or skin. But as I said, the number of the participants was insufficient. So we need to get data from more participants, and they need to generalize the result in future. Next, I'll talk about the sensor and actuator. As I said, inside our skin, there are many types of tactile afferent, and they are densely located, like this. To mimic the tactile performance of human, it would be better to mimic this structure. So for this purpose, I applied the liquid metal small strain gauge as a sensing element, like tactile afferent here. This picture shows a fabricated device. Inside the silicon rubber skin, there was a narrow and small liquid metal strain gauge sensing element. The width of the strain gauge was, I think, less than 1 millimeter. And it is possible to densely distribute the sensing element and placed there at various locations. To form narrow strain gauge, so we focused on the plastic wire for the mold. It is difficult to make a narrow and small liquid metal strain gauge. To solve this problem, we found a way to form the small channel using the plastic wire. So put plastic wire in the uncured silicon rubber. After rubber was cured, so we put the wire. Then the hollow channel was formed. By fitting the liquid metal in the channel, it is possible to get the liquid metal strain gauge. To characterize the strain gauge, so we conducted experiment. In the experiment, we indented the sensor with an indenter with a contact area of 5 mm times 5 mm. So indentation speed was 1 millimeter per minute, and the indentation displacement was 1.7 millimeter. In the experiment, we tried various locations. First, we indented the strain gauge directly, I mean the top of the strain gauge. Then we changed the distance between the strain gauge and the indenter. First, we set the distance 3 mm, next 6 mm. This figure shows the experimental result, and the vertical axis shows the change in the resistance, and the horizontal axis shows the applied force. From the result, the resistance of the strain gauge was decreased as the applied force was increased. When strain gauge was compressed, the length of the strain gauge was decreased. Also, the cross-sectional area of the strain gauge was increased, this side. And this resulted in the decrease in the resistance. But interestingly, here, resistance was increased. That was from the structure of the strain gauge. This area, top side of the strain gauge was compressed, and the cross-sectional area was suddenly decreased. And this results in the quick increase in the resistance. Yeah, this shape was from the structure of strain gauge. And as this distance between the strain gauge and the indenter was increased, the sensitivity of the strain gauge was decreased. A similar trend is seen in our body. For example, the distance between the indenter and the tactile afferent is increased. The sensitivity, the activity of the tactile afferent is decreased. So from this result, the sensor and the strain gauge have similar characteristic as that of the human skin and the tactile afferent. In the future, so we will densely array this small strain gauge inside the silicon rubber and at various locations, and try to mimic the function of human skin. I also focused on the interesting characteristics of skin, so healability. Here, so we fabricated the optical waveguide type tactile sensor. Usually, to make tactile sensor, we try to make the soft material conductive by adding small conductive powders. But sometimes this causes problem. The performance of the conductive powder usually unstable. To solve this problem, so we focused on the principle of the optical waveguide. So we put the diode and transistor and monitored light from diode using the transistor. So the body was formed using self-healing polymer. So when the polymer is cut, it is possible to heal by connecting and at room temperature. After the healing process, it is possible to stretch again. Okay. Here, so I explain the principle of the optical waveguide. As I said, the transistor detects the light from diode. When force is applied to the sensor, the shape of the sensor is changed, and this causes the change in the incident angle of the light, and this results in the reduction of the reflected light here. In other words, so more light passes through the interface between the sensor and air. And this results in the decrease in the light intensity here. So by monitoring the change in the light intensity here, it is possible to estimate the applied force. So we conducted experiment to characterize the sensor. In the experiment, we indented the sensor. And then so we monitored the output of the sensor. So the speed of the indentation was 1 millimeter per second, and the displacement was 1.7 millimeter. After the indentation, so we cut the sensor, so damaged, and then repair. Then we conducted experiment again to evaluate the healability of the sensor. And this figure shows the experimental result. So vertical axis shows the change in the output, and the horizontal axis shows the applied force. The output of the sensor was decreased as the applied force was increased. The result well agreed with the theory I explained. Also, we tried the simulation using the finite element method analysis, and we observed similar trend. But we need to compare the simulation results and the actual results. Currently, we are working on the comparison. So, and the color means the difference in the timing. So blue means before repair, and red means after repair. The sensor output was slightly changed. This was because the sensor was not perfectly repaired. So if we can perfectly repair, two lines should be matched. So currently, I'm thinking the mixing the sensor and actuator. Last year, so I developed a pneumatic actuator using a self-healing polymer. So I'm thinking about the integration of the sensor into the actuator. If so, we can integrate the sensor and the actuator, we can develop perfectly hearable soft robot. Currently, I'm thinking, but it is also my future work. So last, I'll talk about the tactile device technology. In virtual reality, pneumatic actuator is often used to present force sensation. But as you know, the pneumatic actuator require large system, including the pneumatic compressor and the pneumatic valves, and this makes the entire system bigger. To solve this problem, so we focused on the low boiling point liquid, Novex 7000. This liquid is evaporated at 34 degrees Celsius, so boiled at low temperature. So we put the liquid in the plastic bag and heat and cool using a Peltier device. So liquid is heated and reached at the certain temperature. The liquid becomes a gas. Then pushing force is generated. By cooling, we can reduce the pushing force. The entire system is 1 centimeter times 1 centimeter, so too small. It is possible to put this system to the fingertip. This is the actual video. Under the plastic bag, there is a Peltier device. By heating the plastic bag, it is possible to generate pushing force. To characterize this device, we conducted experiment. In the experiment, we heated the liquid and measured the pushing force. This figure shows the experimental result. Vertical axis shows the generated force, and the horizontal axis shows the time. The maximum force was around 1.2 Newton, but it takes a long time to reach the maximum force. From the results, the response of the device was not so good. But on the other hand, we got interesting result. We applied this device to the user interface. So we recruited 10 or more participants, and we conducted experiment with them. So we asked them to put their finger on the device, and we heated the device. And we asked them to answer the timing when they feel the force from the device. And this figure shows the result. Vertical axis shows the pressure inside the device, and the horizontal axis shows the time when they feel the force. Interestingly, the participant can feel the force in about 2 seconds. So very, very faster and quicker, as I expected. The reason for the result is the sensitivity of the fingertip. So fingertip is a sensitive part in the body. Therefore, the participant could feel the small change in the force. So if we can optimize the device structure or heating mechanism, I think it is possible to present the force less than 1 second. And it is suitable for the virtual reality application, but it is also future work. Okay, last, I'll talk about the message. So as I said, inside our skin, there are many tactile afferents, a nerve, and from the signal from these tactile afferents, we can recognize tactile sense. So recently, interesting result was published. Our action caused the unique skin deformation, and the skin deformation also caused the unique pattern, unique response pattern of tactile afferent. According to the pattern, so we recognize what we are doing, or what we are, like how we smile, or how we bend our arm or something. So I want to apply this kind of the findings to the development of the novel devices such as novel tactile sensor or novel soft robot or novel tactile devices. I have been thinking about this kind of topic for a long time, but I have never found a good idea to apply this kind of idea. So if you have a good idea to apply this kind of findings to the devices, please try and show the application to the world. These are a summary of this my presentation. Thank you for your kind listening.
I think you had already questions.
Thanks for the talk. My question was on the fMRI study in your first part. I was wondering, why did you choose to simulate with passive touch on the palm as opposed to like active touch with
Yeah. I see. Thank you for your nice comments. So usually this kind of research, so we use a pin array type tactile device. So I check the related study and I choose the design. But as you said, it is possible to use actuator like this. But in that case, the structure of the actuator might be more complicated, and maybe to control the actuator, we need to put more sensors inside the actuator. Then, so we might require magnetic material to control the system. And in functional MRI, it is impossible to use magnetic material. So that might cause problem. So I think your idea is nice, but if you want to use the idea, we need to consider the structure more carefully.
I mean, I've heard of like really tiny fluid like tactile arrays too. They can like send up a jet.
Yeah, sorry, misunderstanding. Okay, that is a good question. So the reason why we selected push type actuator is ease of the recognition. Because the push force is strong and easy to distinguish. I think the stroke force is not so strong, I think. No? But maybe ease of design of the system. Of course, there are many possibilities for the system.
Of course.
Other questions?
Thank you for your presentation. For the last device that you showed,
This
have
one?
Yeah, this one. Is it made of the self-healing polymer that you use, or is it not self-healing?
Sorry. In this study, so we use a plastic bag because there was a problem of the gas permeability. Of course, we try to use flexible material such as EcoFlex or PDMSL or something, but when I use these kind of materials, there was a problem of the gas leakage. So we encapsulated the liquid inside the silicon rubber membrane bag and heat. Then the gas pass through the membrane because of the gas permeability of the membrane. So we selected the membrane with low gas permeability, like a plastic bag.
But do you think with new materials it is possible to make it also self-healing?
Yeah. But in that case, we need to consider the gas permeability of the material. Maybe usually the gas permeability of the stretchable material is high. So in that case, it is difficult to apply this kind of the stretchable material to this device. But if the permeability is low, it is possible to apply.
Thank you very much.
Other question?
Thanks for your nice presentation.
Thank you.
I'm very interested in your fingertip modeling. Did you consider, if possible, to sense the difference with the liquid and solid? Because I saw it's definitely possible to sense the solid surface, right? But our fingertip, it can also sense the liquid, like water.
Yeah. Maybe I had a similar comment from in your PhD defense. Okay, I think it is difficult because I think when we put the sensor to the liquid, I think the sensor didn't detect the force from water because the water is not solid, and I think the response force from the water is too small, and the sensor cannot detect. One possible solution is the use of the another liquid, such as temperature sensitive liquid like graphene liquid or something. So if I want to use the sensor liquid, it would be better to add another temperature sensitive material in the channel. Thank you.
Thanks a lot for the nice presentation. I have a question on this
Okay.
design. So the idea is then later to make an array structure. Now in literature there is a lot done on like grid type structures to make like a large area sensor, and you want to do it with like vertical sensors. So for me it's a bit unclear what the true benefit is of putting them in like a sort of 3D structure, because it becomes thicker and I think a bit more complex to fabricate. But maybe on the sensitivity it has benefits, but it's a bit unclear to me.
You want to ask the benefit of this design?
Yeah, in like an array structure.
Yeah. Okay. Usually, as you say, the sensor is flat.
Exactly.
I saw the many flat, flexible tactile sensors. Yeah, actually here, so I tried this kind of sensor with Ratsur. Yeah, you are right. But in this research, so I want to mimic the structure of skin. So I want to mimic the layered skin structure and the nerve structure, like the, how can I say that, long nerve structure and so on. So actually it is hard to explain. I have no idea for the benefit for the sensor design, but I believe the design will contribute to the idea of mimicking of the skin structure.
Yeah, okay. But I think it's interesting because anyways, if it's done in biology, maybe there are some benefits
Yeah.
to have this structure.
And I think the process using the plastic wire will be helpful to develop the devices.
Okay, thanks.
Thank you.
Other questions?
Yes, thank you also from my side. Thank you for the nice presentation. On slides 16, 17, 18, you presented
16.
finite.
Okay.
Yes, sorry if I'm a bit fast. Yeah, so these models indeed. I'm just curious how you constructed the models of the fingertips specifically, and how you ensured that it was representative of a typical human finger. So could you elaborate on that?
Okay. First about how I design
Yes, the model specifically.
model. Okay. I check the actually the dimension of the finger is opened. So I refer the size of the finger as shown on the website or journal paper, and design the model using Adobe Illustrator, and put the model data into the simulation software, and generate mesh elements of the model, and conducted simulation.
So maybe I didn't understand. So you found the model somewhere online? Is that what you said?
It depends. For example, okay, I prepared this model. My student prepared this model by himself. But actually, it is possible to buy a model from company.
Okay.
So there are many ways.
Okay. All right. Thank you.
Okay.
Hello, Hiroki. So it was really nice
Thank
working
you.
with you. And after meeting you, I realized that I should call you Sensei Ishizuka. So that's like a respect. So I have a question in slide 18.
18,
So,
okay.
yeah, sorry, 19.
19.
Yeah. So when you model for 2D and after for the future work, you consider to make it 3D, and you say that you want to make it shear, you want to measure that. How would you measure that in that case for shear using such model?
You mean the actual activity of tactile afferent?
Yes.
It is possible to access the data from the other papers. So I refer the data from the papers and evaluate the accuracy. For example, so the result of the tactile afferent, distributed tactile afferent, was shown. So I'm thinking about the comparison with the simulation result and the data of this paper. Actually, to develop better model, so I need to collect more biological data, as I said.
Thank you.
Thank you for the nice presentation. And my question is about the area of application. I think you made mention of virtual reality.
Application is of the
Yeah, of the sensor, yes.
Okay.
That's virtual reality.
Yeah.
So is that what it is being designed for? As in, is that the only area of application that this, the tactile, device is for?
So sorry.
As in, is it only for virtual reality applications?
Yeah.
Okay.
No. Okay, so I think the application of tactile technology is so many. For example, virtual reality is one application. And for example, the remote operation or training or education or something, it is possible to apply the tactile technology to various fields.
Okay, the reason why I'm asking is when you consider prosthetic devices, especially the hand prosthesis, they are, now works on trying to, should I say, bring the way the human skin feels like, trying to have the same structure on the prosthetic hands.
Mm-hmm.
Yet, so looking at, just making reference to the question that previous colleague just asked about the structure of the sensor, I was just thinking of, do you foresee that this design would have to be, in a way changed in order to be adaptable for application when it comes to prosthetic hand? Because if you look at this, is like the thickness of it is significant, but then if you are looking at the prosthetic hand, how do you think this design can be applied in?
Yeah, good question. So for the robotics, I think it is not necessary to mimic the skin structure because the robots should be optimized to tasks. So in that case, I think we don't need to mimic the structure. But if we want to correct and understand the tactile sense, so we should mimic the structure of the skin and develop a sensor and collect data and analyze. Then so we can understand how we feel from the texture or object or something. The structure is contribute to the scientific side and the understanding of the tactile sense, I think.
I think it's exceptional that almost everyone asked a question.
Okay.
So I cannot stay behind and I was waiting and they were always new. So you developed quite a lot of hardware, and in pure Flanders we have not to say pressure, but the quest that it's also valorized, that it's exploited, that it goes to the market, or in collaboration with other companies, or like we do making spin-off companies. How is this for your work in Japan? How is this relation with companies, startups, and bringing your innovations to the market?
Generally, the researcher in Japan try to make a company if they can get good results. Actually, my colleague has a company for the contact tactile sensor. Of course, my supervisor also launched a company for the taste device. But for me, so I really like writing a paper or discuss the research. So currently, I don't think about the company or market. But in future, as you said, I need to consider. Also, the student from the company asked me to consider about the launching company. So he was from company and 6 years old and many experience. So recently, he said the researchers should think about the market of the technology. That is my future work.
Yeah, and so do you have patents or you make it open source available? Because in our labs, we do a bit both, where sometimes we protect our patents, but otherwise we sometimes think it's maybe serving better the community by making it open source.
You mentioned about the patent.
Yeah, or patent, but also like open source. So we have also
okay.
tutorials on source.
Okay. Okay, the devices are not open source, and I had one patent, but not for this research. So I need to think about the open source or patent. Actually, I'm just thinking about the patent using for the self-healing polymer. So last month, I talked with the research associate, and now so checking the related works. So I started to think about the patent. So as you said, I need to think about the company or the patent or the open source. Yeah, that is good view. Thank you.
Thank you. Other questions? Then I think we can conclude here. Thanks a lot for your presentation. Yeah. Thanks also for your research days here. And have a safe trip back to Japan. But first, maybe we can enjoy the lunch together. So thanks a lot again.
Thank you, Bram, and all.
Thanks, and team for the online. Yeah.